Hello, welcome to one more lecture of our course on fundamentals and biomedical applications of quantum science and engineering. Well, in the last lectures, we made a full explanation about why is quantum concepts important for science in general, especially the technological science, especially for applications, and start to give you some concepts. So the first general concept that we gave was waves. And why we have done that? Because waves will be very important for the interpretation, for the understanding of the concepts involved on the fundamentals of quantum science. But that's not all. There are even more fundamental aspects that we have to kind of make a revision before we really start to give you some quantum effects, historical facts, and how this wonderful science was built up. Okay, so today we're going to start, as I announced in the very beginning, in the first lecture where I give you an overall map of our course, we're going to speak a little bit about probability. Right? Probability is something that everybody speaks about, everybody uses, even the ones that never studied uses. You know, it's very common, people say, well, the probability for is that. They guess something. And they know what probability is. And today we're going to elaborate a little more. You know, of course, we don't want to be heavy mathematical in probability, but we're going to explain a few things because there is a mathematical language for this concept. We have to somehow quantify probability to be able to use in the construction of the quantum science. So basically, as I said in the very beginning, waves and probability are two important concepts we need to know in order to understand quantum science. Okay, so today's lecture will be them still in general concepts, so we're still going to make a kind of revision, but now will be about probability. We want to build up some ideas about probability for you. And why we need probability? Well, we need probability because the things are not fully certain in nature. You know, normally many things, they have uncertainty. They can be one thing, they can be another one. You know, there is a lot of random things that happens in nature that make us to be able to somehow understand or to be able to predict, in fact, to construct this concept. This is not a new concept. It's not something that happens in the last decades. It's been created for the last century and even before. People already gamble, and a gamble, you know, you want to understand the chances you have to win. And of course, you have to learn in your mind how to estimate such a things. And then that's the concept of probability. If we want to define a probability in an easy way, I would say is a measure of uncertainty. So whatever we have uncertainty, we need the probability to somehow deal with the problem. In many situations, there are many possibilities. And if there is many possibilities with the equal frequency or not, right, then probability is necessary to describe situations. Let's take an example. And that is a very famous example because we see every day on the TV and everything, which is the prediction of the weather. You know, you're going to predict the weather. You're going to say, well, is that going to be cold? What is the temperature? And of course, you know that, well, that is not one chance for the temperature. It may be many things. Speaking about Celsius, which is the civilized language for temperature, or is the one adopted internationally. But we can speak about Fahrenheit as well, which is a good unit. You know, you can predict, but in an interval, there is a big uncertainty. So normally there is probability associated with that. Now, weather, for instance, is one of the things that is an example of things that are uncertainty and you need the probability to deal with. But how we quantify, the quantification of probability, well, the number that's associated with probability, normally is related to the frequency that certain event will appear how many times. So suppose we're gonna say, well, how will be the weather for the week? So we're gonna have rain for Monday, Tuesday, and Wednesday. So out of 7 days, 3 days will be raining. So you see, there is a frequency associated. It may be that will not rain, so it's a probability. It may or may not. But if it does, and if we are able to sampling, we're gonna get around those numbers. So the frequency of one event out of many possibilities is what we define as probability. So probability is a number that helps us to quantify things. This number helps us to tell the frequency that some event will happen out of an ensemble of possibilities. That's the probability. Okay, so when we say it's going to rain, you're going to answer yes or not. So this is 0, 1, right? And this is discrete. Discrete is when you have specific things. But if I ask how much is going to rain, right? It's going to rain like a liter or a few cubic centimeters, or normally they measure by height, right? They measure millimeters of rain. And then that can be anything from 0 to some number and goes continuously because so probability in general can be discrete when the values are very determined, or can be continuous. And that's what's interesting in probability, because you have these two possibilities, and we have to somehow learn a little bit about them separately, when they are discrete or when they are continuous, right? The quantification of this concept of probability. Okay, so actually, probability provides us with a way to deal with the uncertainties, right? This is a good message. We're gonna have events that has some uncertainty associated with it, and we have to somehow to calculate that, and then we create this concept of probability, which is a logical and reasonable way to deal with this. So normally, to have a probability to be important, you need uncertainties. You need to have many possibilities of something that you do, a measurement, for instance, and or observation, and you have to have uncertainty associated with it. When that happens, the situation is best described by probability. And knowing the probability, knowing concepts associated with probability is very important. Why is very important? Because it helps us to predict things. You know, that's the way that weather is predicted. People work with probability. They learn how to deal with what they observe, with what they can say. They can predict, but they can predict with some probability. With some, because many things can interfere, many things can happen. So the best they can do is using the conditions. They know many things that can happen, and then they comes with this concept. So probability is nice because they help us to predict. And when they help us to predict, they help science, because we construct a theory and we want to be able to predict situations, right? We don't want to only understanding what we measure. We want to be able to take what we measure, construct a theory, and then be able to predict. And to predict, we need the probability. And that's the strength of quantum science, is that we learn the concepts, we learn to predict the things. And that's why people can design new drugs, can design many things, because they know today. Or even project new materials that nature do not provide us. but they know because they are able to predict what properties that will have, and they are able to somehow using the tools and predict things. That's very good in probabilities, prediction, right? And some people are so good on that, they can go to a game, a table game, like poker or cards and many kinds of games, and they can more or less be able to read the conditions and predict things. Okay, we're not going to do a full course in probability. Even though it's wonderful, engineering should know a lot about probability. But what we're going to do instead is give you the concepts so we can go on with the quantum science and with the concepts we have. So you see, I'm putting waves together with classical mechanics of mass together with probability. That's what we needed to put, to cook, and to come out with the quantum concepts. Now, if we're going to construct the quantum concepts, it's nice to start to define a few things. So this is what we're going to do now. We're going to start to define some concepts that are very important on the construction of these probabilities. First thing we have to tell is the concept of sample space or sample size. What is a sample? A sample is everything that can happen in probability, all the possibilities. So we were speaking about the weather. It's going to rain or not rain. It's going to snow or not snow. Or maybe if we speak about weather, we could say it's going to have sun, it's going to rain, it's going to snow. So we have three possibilities. Just speaking about those possibilities of events. So my sample space is composed of three possibilities. Of course, only one of them will happen, and will happen with some probability. They are equal probability, not most of the time. Most of the time, if you look the conditions around, you are able to predict that some of them will be more frequent, will be more probable to happen than others. And that's what we're going to learn. But we're going to have to deal with this sample space. Sample space is everything that can happen. So it's all possibilities that you're dealing with. All possibilities. And normally we call S of sample. So when I say sample, means I'm dealing with all possibilities. Right? So all possibilities is sample. And we're going to call S. And we quantify, right? As I did with the weather. Now, there is another concept we need to learn, which is event. What is an event? An event is any possibility that happens out of the sample. So any possible collection of results from the sample is called event, right? Any possible collection. Now, one event can be the three of them, not for weather. Weather either going to rain or having sun or snow. You can't have both together in one place. But in many cases, you're gonna see, situations where I can have two things happen together. This is possible because they are predicted inside the sample. They are possibilities, and putting them together is also a possibility in many different situations, not the prediction of the weather, but in many other things. An event, normally we call A, but we can call B, we can call anything. So this is just like a literary way of represent sample and represent event. So you already learned these two concepts. Sample is everything that happens. Event is some subdomain of the sample. Well, it can be the total thing. I can ask it to you, well, if it is going, I accept any event like it's going to rain, snow, or sunshine. So I create an event that can be any of those three, which coincide with the sample itself. It's okay. You know, we all know that one set is subset of itself, so it's fine. Okay, very good. So we knowing already the concept of sample and event, then we can define the probability. So let's define the probability. Probability of an event to take place. So the probability of some event, any event, here I call A, but can be anything, is exactly the ratio between the occurrence of A divided by the total sample, right? If the event I'm looking for is a tiny little thing inside the whole sample, then this will be small. Now, if this event is a big part of the sample, then this probability will be big. So you see, we go from a qualitative concept to a quantitative concept because this will be a number. This will be a number, and its number is what defines the probability. So I know that we all learn this in many different parts of our education. Some learn in high school, some learn in elementary school. But so the probability of an event is the occurrence of that event divided by the total sample. So if you repeat, or if we let the sample to manifest itself, if I look how many times the occurrence of such event takes place divided by all possibilities that could take place, this is the probability. And it's a number. So we quantify that way the chances of something to happen, which is dealing with the uncertainty. And this is the probability. Now, we have to put some properties of this probability that we are defining. One of them is always positive. You know, some people claim negative probability, but not in the universe we're going to work. In the universe we're going to work, all the probability is positive. Okay, here there is a tiny little mistake of the positive. You know, you never worry about too many spelling because, you know, this we can correct. We cannot correct concepts. This is hard to correct. Okay, now, probability is always positive. Probability, it cannot be bigger than 1, right? Because, you see, there are many chances. S is always bigger than A. S is all possibilities. A is a part of the whole possibilities. Therefore, S is always bigger than A. At the most, it can be equal. So, probability is bound to an interval that goes from 0 to 1. If my sample and my event coincide, right? Suppose that my event coincide with my sample. Then the probability of the whole sample is equal to 1. If I am consider all possibilities, the probability is 1. And that is something else. When you have the events, and they are somehow independent, but they may have different occurrence. So, you know, I may have 3 events on the prediction of the weather. But maybe each event having sunshine, rain, or snow, they occur with different frequencies, and that's true depending on the season, right? Depending on the time of the year. then they're going to be different. They're not going to be equal each other. They are not equally probable. So each event that I take from the sample may have a different frequency of occurrence. So they may end by having different probability for that specific event. Let's say that in my sample, let's say that my sample, all possible events makes the sample, right? This is what we said. So capital AI is a specific event in my sample, right? I hope you all following this mathematical way of expressing things. I'm kind of mixing qualitative concepts with quantitative concepts, but they are very easy, right? So if all the possible events makes my sample, then each of them has an individual probability. And what I was saying a few seconds ago is that the addition of all possible probabilities of all possible events must be added to be 1, because they make, when I cover all possible events, I cover the whole sample. That means that from the sample, always some event is going to happen, right? So and if I consider all possible events, there is a fully certainty that that will take place. That's why all the probability adds to 1. So this is like 100%. Of course, you can take this value and multiply by 100, and normally this fraction will be expressed in percentage, which is common to do in many situations, right? So knowing that those properties apply for this probability, you know, it is positive defined. It goes between 0 and 1, including 0 and 1. The whole sample is 1, and from consequence of the whole sample being 1, the sum of all probabilities must be 1 too, because here covers everything that can happen. Therefore, that add together is 100% to take place, right? If I say, okay, what is the probability of either be sunshine or be raining or be snowing? See, I said anything I accept. What is the probability that happens if these are the 3 possibilities? We could say a cloudy day, but you know, I mean, we understand. So we create a sample that doesn't include that one. It's 3 possibilities. When I say I can accept anything, what's the probability of this take place? Then it's 1, right? It's 100%, because one of them will be there. It's probability is always nice to illustrate, to have example. And I'm going to give some examples here. So let's assume an example. We're going to flip 3 coins, or we're going to flip at 1 coin 3 times. It's the same. In a row. So take a coin, you're going to flip, right? So you have the coin, you're going to flip. It can be either head or tail. And then we're going to count the number of heads. Count the number of heads. What is the sample we have? Well, as you see, things can be head or tail, H or T. I may flip 3 times the coin in a row, and then I have no head, 0. But I may have 1, I may have 2, or may have 3. So even though I have flipped the coin 3 times in a row, my sample has 4 possibilities to take place. Right? These 4 possibilities is exactly my sample. So that's my universe that can happen. and one of them will happen. So let's create now in a graphic way these possibilities. So I may have here, I'm putting what's happening in the first flip. So this is the first flip. That's the second flip. This is the third flip. What's happened is I may have head followed by head followed by head. I may have head followed by tail. I may have head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. Tail, tail, tail. Of course, this corresponds to the 0 here. There was no head on it. But it's a possibility that can take place. Now, we're going to calculate the probability of 0 head. Then I have 1, so the occurrence is 1 in my sample, divided by 8, which is the total possibility, number of possibilities. This is number 8 possibilities. So it turns out to be 1 divided by 8 when I apply my definition of probability. So this is the probability of have 0 head. Now, I want to have 1 head out of my experiment. Then I come here and see how many occurrence with 1 head. I come and say, you have to look for the ones that has only 1 edge. So I have 1, I have 2, I have 3. So the frequency of the 1 head in my sample is 3, and the total number of my sample is 8. So the probability to have 1 head out of my experiment is 3 over 8. Then I ask, what is the probability to have 2 heads? Well, then I come in here and see what are the frequencies that 2 heads appear. And you're going to see that's 3, 2. And then 3 divided by 8 is the probability. And what is the probability of have 3 heads? Of course, 3 heads is only 1 possibility, so I have 1/8. You see, what that number means? That number means that to get 1 head, when I flip out of 8 times experiment, I hope I'm going to have 1 0 head. And so on. You understand? So if I keep repeating this will be the percentage that those results will appear. That's the concept of probability. So when this number is big, like 3/8 is bigger than 1/8. So that is 3. When I flip this coin many times, and I see that 1 head appears 3 times more frequent than 1 head or 0 head, equivalent to 2, and of course 1 or 2 appears equally, which is very interesting. The chances to have 1 or 2 is equal. And if you add up everything, turns to be 1. Because when I add all those possibilities, so if I make the sum of P0 plus P1 plus P2 plus P3, which are all the possibilities of my thing. This composes itself the sample. This is one, as you can see, by adding that up. Okay, so see the example and the quantification, what's going on. I'm gonna flip the coin only 3 times, and then somebody from outside is going to observe. Of course, only one thing is going to happen, but with a chance, because if I flip the coin 3 times, many, this will be the percentage of the appearance. Okay, so you see, we are constructing already this nice concept of probability. When we have a sample, we may have an event, and whatever is left from the sample is what we call the complement of that event. So this again, if I'm going to represent graphically in an illustration, what is the event and what is the complement. The sample is everything, so it's everything inside this box. That's the sample. But we took one event, is one subspace. So when I took all the possibilities in my last experiment, I said, what is 3 heads out of 3 flippy coins? It's one event. So this is a one event. And I only care about this event. I don't care about the others. If that's true, I only care about this event. I don't care about the others. So I separate my sample in 2 pieces. One it is my event and the rest. And normally this is called the rest. This is my event. I chose it to be something like 3 heads in a row. And the rest of it is called the complementary event. So that's when I add the complementary event with the event I chose, I make up the sample. So everything else that happens out of that event is the complement of that event. And then there is a very nice rule, is that the probability of one event and the probability of the rest of it make the sample, so make one. So sometimes I don't know how to calculate the probability of something, but I know to calculate of the probability of everything else, which is the complement. And the probability of the complement is exactly 1 minus the probability of the event, right? So the probability of everything else is 1 minus the probability of that event. And it's very useful most part of the time, as you're going to see later. Now, before we end this first part, let me introduce to you what we call sequence of probabilities. You know, because what we're doing, flipping 3 times the coin, is a sequence, right? And there are some nice rules for the sequences, and we have to understand how to do. Normally, they are independent, because if I flip a coin and I come and flip again, there is nothing that will interfere in one flip and the other flip. They are fully independent. That's what we call independent procedures or independent events. So we want to know, and that we use a lot, is what is the probability of a sequence of outcomes. Exactly like the way we did. Because, you know, flip the coin is always the same experiment. So it's like always the same event. I flip the coin and I can have head or tail. And then I flip the coin many times on a row. And we can prove that actually if I flip the coins any times, I flip any times the coin, the probability of have always the same result, like having always head, and head, will be the probability of one of the single events to the power n, which means I am multiplying the probabilities. So this is a very interesting result, because the probabilities multiply themselves. They add up too when I accept one or, because I'm taking different events. Now, when I consider the same event and do many times in a sequence, they multiply, right? And this is an important kind of rule to know. It's very natural, because they build up. The probability always is smaller than 1. To the any power is much less than 1, right? But this multiplication rule is very important, as we're going to see in what follow. Okay, now let's do another illustration. In fact, I'm taking the same illustration as before. We flip 3 times the coin, and the probability of obtaining 3 heads in a row. The probability of one event, I flip the coin and I have one head, is half. As we know, because there is only 2 possibilities in one coil flip, right? It's either head or tail. But to have 3 in a row, which means what's the probability of having had, it's just multiplying the probability of having one head, because each of those experiments is a sequence of independent events. And it's 1/8, as we have obtained before. If you compare from the examples, we got 1/8, right? And this is important, and it's called multiplication principle. And you have to keep that in mind. Because why we never make good money in the lottery, only a few, because each number you take out, now if you replace the numbers, if you let them to repeat, to make a digit, to make a full number, they are independent. If you have 10 digits, 0 to 9, and the probability of get each one, each time you select a number, is 1/10. But when you're going to make a million, which means 4 digits, or 3 digits at least, right, means that you get 1/10, 1/10, 1/10 3 times. Is 1/10 to the cubic to make 3 digits in a row. So it's 1/1000, right? And if you get more numbers that multiply, that scales up very easy, like in a power. And then 1 out of a million may get the prize when you put a big number, because the independent probabilities multiply. Now, if you take 1 out, then you have to multiply with the right, with careful. Because if I have 90 digits, each time that one comes out, I don't replace. Then in the first experiment, I have 1/10. But then in the second, I have 1/9. In the third, I have 1/80, and so on. And this number is different. And then we're going to learn that later. Okay, so we are getting 2 probabilities, right? And let me give you another example, because, probability is something that comes to our intuition. That's why many people know probability without not even study that in any time of their lives. But it's intuitive what's going on. Okay, so we're going to do another example here. And this example is we roll 2 dice. We're going to roll 2 dice. What's the probability to have as a sum of the numbers that appear? The number 10. Okay, so the thing is very easy, because I roll 1 dice. I have 6 possibilities. And then I roll again the dice. I have another 6 possibilities. The total number of possibilities in my sample is 36. Right? Of course. Easy to know. 6 times 6. Now, what are the results that add up 10 when I sum the numbers? Well, I can have 4, 6, 5, 5, or 6, 4 in the dice, which means only 3. So the probability to roll 2 dice and have the sum 10 is 3 out of 36. So the probability is 3 divided by 36, which is 1/12, right? Again, the intuition says that if I repeat my experiment 12 times, probably in one of them I will get this. If I throw only once, it's very small, less than 10% chance to have the sum giving 10. Now, if I repeat 12 times, probably one of them will be, the sum will be 10. I guess you understand, you're getting the spirit of the probability, right? Okay, now there are many things that I'm gonna pass very, very fast, because probably you know already, which is counting permutation possibilities within a sample. And I just want to recall you this. I'm not going to make a big deal, but there are concepts that are important in probability. One of them is counting permutation. Suppose I have a sample that has many possibilities, and then I say how many permutations I can do, right? So if I have any elements, the number of permutations that I can do is any factorial. Remember, any factorial is any times any minus 1 times any minus 2, blah, blah, until 1. This is the definition of a factorial of a number, right? And normally we define 0 factorial as 1. If we wanted to permute groups of k elements out of n, suppose I want to take out of here, suppose I want to take out of my elements groups that has k elements, but originally I have in my sample n elements, but I want to select k elements, groups of k elements. So I want to permute groups of k elements out of a sample of n. This is any factorial divided by any minus k factorial. When n is equal to k, of course, is the how many permutations, how many changes you can do in the sample, full sample itself, and then this is 0 factorial, which is 1, so you get back the any factorial that I told you is the number of permutation in the whole sample. But when you select only k elements out, this is something that this belongs to what we call combinatory analysis that we learn in many courses, and they are important, right? So this is something that sometimes we use, so I said, well, let me throw in here, because if we need, we go back to it in the coming future. And I did not prove anything here because this is just a small revision. Counting subsets, that's also important, and is the last thing I want to say about this. If you're going to count subsets, means out of my sample, I have a sample of any elements, can be anything, any elements. The number of different subsets of size k that we can construct from S is this number, is any factorial divided by k factorial times any minus k factorial. This is something also very common in combinatory analysis, and it's just playing with numbers. So suppose I have, what we were discussing about weather, and then we can have a cloudy day, we can have a sunny day, we can have a raining day, we can have a snowing day, we can have a very cold day, we can have just a warm day. So I create a sample. And then I say, well, what are the possibilities of being sunny and cold? And that, I can make this extract from here, different subsets. And then I can see how many subsets I can create in general. And this is important when we deal with numbers and deal with everything. Okay, well, we didn't finish yet this revision of probability. We need one more lecture for that, and to speak about distributions, which is the most important concept that we're going to use a lot in the quantum science. But I'm going to do that in the next lecture. So please don't miss the next lecture, and see you there. Bye-bye.